Hello, good evening. So, thank you for joining this session. My name is Parth Joshi. So, I'll be conducting this session for today. So, I'm just waiting for more people to join. So, I think we should get started by in another 2 to 3 minutes. So, good evening, all. To those who have joined, I'll just wait for 1 more minute. I'll see, like, let's see whether anyone else is joining, and then we can get started. Hello, hi. So good evening all. So thank you all to those who have joined. Uh, my name is Parth Joshi. So I'll be conducting this online session on this course on modeling and simulation. So I'm sharing my screen now. So can someone just confirm that whether you are able to see my screen?
Yes, sir. Yeah.
Okay, sure. Thanks. So let me just start that. Uh, about myself. So, my name is Parth Joshi, and I'm a PhD student in the Department of Mechanical Engineering at IIT Bombay. And how I got this opportunity to interact with you is through this Prime Minister's Research Fellowship scheme. So, I am a recipient of this fellowship, and as a part of this fellowship, I got this opportunity to conduct these weekly interaction sessions with all of you. And I would like to thank the NPTEL team for giving me this opportunity. So, in the last week, we had discussed about the basic introduction to modeling and simulation, and yes, I was supposed to actually upload the recording and the lecture slides, but I was actually unable to do that. So, but I will do that tonight itself. Uh, but so those who I think attended like and who may not have attended may have missed. So, are there any questions related to the contents of the previous week or this week before we start?
So this week two, sir, week two or week one?
So any of the like the content covered so far, week one or week two, whichever. Uh,
This bond graph transfer function converting into the transfer function, I not clearly understand.
okay. So
So that is
which part did you not clearly understand?
uh, there are like state variable part, identifying the state variable part, one part.
Okay.
Then integrally causal storage element receiving from the system. That one, that part. It's very,
Okay.
very, very difficult, Philip.
Okay. 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 So maybe we'll try to address some of those parts. And if not, so I think if you could like note down my email ID if required, so you can if you have a detailed question or something specific question, so you can always email to me directly whatever your questions are, or you can post your questions on the so I am entering my email address over here, so you can actually note this down. And so if you have some like detailed very detailed question or specific questions, so we can actually uh, have a separate meeting also for this, or I'll try to answer those over email also. But
Okay, sir. Thank you.
yeah, so can you just repeat like which part like you were not like you did not understand clearly?
So the part one is spring which connected with the register and one coupling, that part. That part.
Sorry, I did not get your question. Sorry.
Actually, I have to look the slide again which part because I have noted here. I cannot understand. I know the question, but it's difficult to express the representation that figure also.
Okay.
Because one, yes, sir. While studying, I will say, sir, I will interview. While if that stage come, then I will tell you.
Oh, okay, fine. So whatever. Okay, so what we'll probably hopefully try to address some of your questions in the things that we are about to discuss. Hopefully that will answer some of your questions. If not, so you can always contact me on this email ID. So I'll try to respond with whatever best possible. Anyone else had any other questions or some comments?
Will we get more examples to solve for bond graph on electrical and mechanical systems, like examples? There were only two, three examples in this slide. It was not enough to understand completely.
Okay, fine. So yeah, so hopefully like some of the things that we'll be solving in today's session will be some examples that you will get to solve, and if you want still more examples to solve, we can I think provide you that uh, definitely. So so maybe I can also add some examples to unsolved kind of examples, kind of problem sets in my slides that I will be sharing after this session. So hopefully that should help you. Make
Thank
sense?
you. Yeah.
Okay. Uh, Fine. Anyone else? Fine. So in the last week we discussed about the basics of like modeling and simulation, and in that towards the end we also saw some how we can use tools like MATLAB uh, to solve these problems, like how we can use MATLAB as a calculation tool to solve some differential equations, etc. And so we saw some demo examples for that. And in this week, we'll be mainly focusing on this technique called as bond graph modeling. So this is essentially a like a modeling technique in which we do not directly go into deriving mathematical equations. So the mathematical equations come up naturally or algorithmically, so to speak, in this process. So we actually try to derive a graphical representation of whatever physical system that we are considering, um, and by that the equations come out of, by itself through that, basically the modeling technique. So so like once we are like have a system, have a clear representation of the system in the form of a bond graph, we can essentially just provide that bond graph to a simulation tool, and at the back end of that simulation tool it will derive the governing differential equations itself through its own inbuilt algorithm. And by that, this will in some sense simplify the modeling process. So it's a powerful technique in the sense that it contains some simple elements uh, to draw bond graphs. So there are set of some standard elements, and these elements are the same across all the domains. So if we are like dealing with an electrical or mechanical or hydraulic or whatever kind of system, so the tools and techniques that we would use are actually the same across any domain. Or even if the system contains, you know, parts and components from different domains, we can still use the same set of elements to represent the system through this bond graph graphical technique. So that is essentially the content for this work and for this week. And the like the another important point that is covered is causality in this week. And once we construct this bond graph model, how can we use it to generate the system equations, that is also been described. And the methods of drawing bond graph models for electrical and mechanical systems have been discussed. So some examples have been covered in this in the lecture slides. So so we can start off with the simple some problems which I have picked up. So those are some sample problems which I have, which we you can expect which are similar to the kind of problems you would see in the assignments. So let us get started. So the first question is shown over here. So in this question we have been given a bond graph where we have this two sources of effort, F1 and F2, and there is a one junction and a zero junction. So the sources are basically connected to this one junction, and this one junction is connected further to the zero junction. So what is asked in this question is that if we are given the magnitude of the forces F1 and F2, then what would be the effort entering the zero junction?
Sorry,
So
it will be 5, I think. 5 Newton.
sorry.
5 Newton.
Someone said something. Uh,
Telling the force entering into effort entering into zero junction is 5 Newton. Summation of F1 and F2.
right. So why do you think it would be the summation?
Because we have to see the direction there. The direction in both side, one in one, it's incoming there, and outgoing is only one, means it should be the addition.
Right, right. Yes. So basically, the property of one junction is that it's basically a common flow junction. Basically, the flow variable is same across the junction, and the force is basically getting added up. So the F3 will be basically F1 plus F2. So that will be basically 2 plus 3, that is 5 Newton. So that is correct. Anyone has any doubts? In the next question, so we are given another bond graph where uh, we have a one junction again. So there is a source effort here which is connected to this one junction, and this is further connected to a resistive, capacitive and inductive element over here. What is asked is which of them is a strong bond. So any idea about that?
Fourth one is the strong bond
Right. So why do you think it's a strong bond?
because it is giving flow to the junction. It is the only component which is giving flow to the junction. One junction is a same flow junction.
Yes, yes. Correct, correct, correct. Definitely. So uh, yeah, so you're right. So it's like a type, one junction in which, so we can see that the uh, causality arrow like that is towards the one junction over here on this side, whereas the causality for the inductive element is on the right side here. So that is basically giving the flow to the one junction. So you are right. So it's the strong bond in this figure. Now here again we have been given the sequential causality assignment procedure. So based on that, like we will be basically assigning some causality in that bond graph. So considering this, so how do we proceed in assigning the causality? So which one would be, so to start with, which would be the first element or bond where to which we will assign the causality?
Uh, Source of effort or
Sorry.
source of effort. Yes, see,
Yes, so we'll be assigning the causality first to the source, and next. So generally for assigning causality, like we have some elements for which the causality is fixed, and in some elements it is based on some desirable causality representation. So, and whereas in some elements we have a flexible causality. So, so we would, when we start assigning the causality, we can, uh, you know, uh, first start with, the ones we know for sure that this would be the where like where do we put the causality arrow or causality, mark on this bond. So, so you're right. So first we will start with the source. So the causality would be at this end for because it's a effort source. So the flow, so the causality mark will be at the end where the flow is being computed. So similarly, we have like different elements over here, which are like inductive and capacitive elements. So I1, I2 would represent the component which is analogous to inductors, and C1 and C2 are the components which are analogous to capacitors, right? So, so any idea about like the how do we assign the causality for some of these elements? So anyone has any idea? So for an inductive element, so we have, let us say, if we can draw the bond like this for an inductor, then we assign the causality bar like this because we write the equation for the inductor as uh, so if, let us say, U is the voltage across the inductor, and then so generally we in when we write down uh, the representation for that, so or the governing equations, we generally prefer writing an integral causality statement rather than a differential one. So that's the general rule. So just a moment. Yes, so for the inductor, so we could write that, the so L di by dt is the voltage across the inductor. Sorry for the disturbance, just a moment. Just a moment, sorry for the disturbance. Yeah. Yeah, excuse me for the interruption because I was getting a call. Yes. So what I was saying is that the uh, the equation that we represent for an inductor, so it is basically uh, L di by dt is basically the voltage across the inductor. But now this is a differential relation. So instead, we prefer to to write it in a integral way rather than a differential way. So so that is the uh, preferred causality statement kind of rule. So so let me just write it down. So what I meant to say is basically that L di by dt is, let us say, the voltage across the inductor. We rearrange this and write it as I is 1 by L into integral u dt. So this is the preferred integral causality relation. And similarly for a capacitor element, so if we draw like the if this is the bond for the inductor, and let us say if this is the bond that we draw for a capacitor element, then uh, so for the capacitor what we get is, so this is the differential kind of relationship that we get for a capacitor now, but we prefer to have a integral causality statement. So we again rearrange it to 1 by c integral I dt. So did everyone understand up to this point?
Yes. Okay.
Okay. So now we prefer to write it this way. So then I is basically what we call it as the flow variable, and U is basically the effort. So we are actually calculating the flow variable from the effort. So that's why we put our causality bar on this right hand side, because it is being calculated over here. On the other hand, U stands for basically the effort variable. So whereas the current is basically the flow variable. So here we are calculating our effort from our flow variable. So the flow variable is our input, whereas in case of the capacitor, so our flow variable is our input. So that's why we put our causality bar over here, because the flow variable is being calculated on the left hand side over here. So that's why we put our causality bar for the capacitor element on this side. Whereas for the inductor, our the equation that we write, so our flow is our output, or basically the current that the inductor is applying, so that is our output that we are calculating. So that's why we put it on the right hand side. So does that make sense?
Yes,
Yes,
sir.
sir.
Okay, sir.
Sure. So, so based on this thumb rule, we just we assign the causality based on that. Now for the resistor, so let us take the resistor. So based on Ohm's law, we let us say if our resistor is this, and let us say if U is the voltage across the resistor and U is and I is the current that flows. So we can write it as per the Ohm's law. The equation would be either U is equal to R into I, or alternatively we could also write it as I is U upon R. So depending on the situation, we could use either of these representations. So in when we say causality, uh, we always say that the LHS would be basically corresponding to our effect, and the RHS is something corresponds to the cause. So generally we are talking about a cause and effect relationship between the input output variable. So it's like in other words we can say like the I is, let us say if in the first case, so I is basically our input and U is our output, or in the this second case U is our input and the what we get as the output is I. So I is basically the output. So so our causality always goes from cause to effect, right? So then that's why we could assign our, like when we draw the bond for the resistor, resisting a resistive element, so then we can assign our causality bar, like either we could assign it over here, or we could also assign it here. So when we assign the causality on the right hand side, so then that means that our flow variable, which is the current, is our output. So we are basically here we are talking about the representation which is I is equal to U by R. And if we assign the causality on this side, on left hand side, then we are essentially talking about a representation which is U is equal to R into I. So this assigning of this arrow would change our equation in this way. So is everyone able to follow that this part?
Yes, sir.
Okay. So this is how we get like can so we can flexibly assign the causality depending on the situation or whatever problem that we have. Uh, and the other rule is we so first we talked about the causality for the inductor and capacitor element, and now we talked also about the causality for the resistor. Now for the the components which are called as sources. So there is a source of effort. So and there is a source of flow. So when we say it is a source of effort, so in any case, so since it's a source of effort, we know how much effort is being provided. So the effort is our input, and the flow would be basically our output. So that's why we assign the causality for the the causality bar on this side, right hand side, because our flow variable would be our output. On the other hand, when we say that it's a source of flow, that is um, it is which is given over here, so then our flow is our flow variable is our input. Let us say the current is a flow variable, or let us say the volumetric flow rate, or whatever, for any problem. So then if that is given, so then that is our input. So the flow variable is being calculated over here on the left hand side. So that's why we put our causality in this way. So this is generally, this is fixed, whereas this is for the resistor, it's flexible. And in addition to that, we have different kinds of junctions, right? So we have a zero junction. So let us say if we have two bonds like this. So let us say we call this as efforts E1, E2, E3. So then for a zero junction, based on its definition, it's basically a constant effort or common effort junction. So which means that E1 is equal to E2 is equal to E3, whereas the corresponding flow variables, so F1 would be basically equal to F2 plus F3. So this corresponds to, let us say, like if we have a pipe in which fluid is flowing in this way, and it's being distributed in this fashion. So then this F1 would be the, let us say, flow rate of the water, let us say, which is coming inside this, and then the F2 and F3 are the flow rates across these two branches. So similarly, if we have let us say some an electrical connection, and let us say this is the point A. So here the this point A corresponds to like the same potential. So the uh, that this point A is equipotential. So this is the one of the ends for all these three components. So this A point is also can be modeled as this zero kind of junction, using this zero junction property, because the effort variable or voltage in this case is the same for all these things. So the voltage at this point is same for all these three components, so that's why we can model it as a zero junction. And the current, let us say I1, which is coming through this resistor, is being distributed into two branches as I2 and I3. So our flow variables F1 is, so basically I1 is analogous to F1, and I2 and I3 are basically analogous to F2 and F3. So this is the the electrically how we can see that, how we can model a zero junction. So does that make sense?
Yes, sir.
Okay. So is this description somewhat helping you understand like this concept of causality in some way, and how do we assign the causality, whatever that I have been talking about? Is this helping you understand how we assign this causality part?
Yes, sir. Slowly and slowly. Understanding.
Okay, okay. Sure, thanks. So, yeah, so since we have this flow equation, so we are calculating this F1 is equal to sum of F2 and F3. So it's like we are saying that F2 and F3 are our inputs and our output is F1. So basically we are calculating F1 at this end. So that's why we assign the causality for this junction on this part. So the our causality bar will be here basically. So for a zero junction like this. So based on our flow equation. Similarly, like how do we see this whether like somewhere, how do we identify a zero junction kind of thing for in a mechanical context? Can someone give me an example?
So we have to look like series and parallel according to that.
Right, exactly. Yeah, in some sense it's like series and parallel. So let's say if we have like this is easy to see in like, especially in electrical circuits, etc. So in like, so if we have something like this, so these two resistors are in parallel, or basically these all these three things are in parallel. um, Now but if like this, let us say inductor and capacitor, so now they are in series, and this point, let us say this is, we call this as A. So this is at the points, like, or basically the voltage across these points A B is same for both these two resistors as well as these combination of inductor and capacitor in series. So so basically the current that is flowing through the inductor is basically this same for both inductor and capacitor. So which is basically same as the equal flow junction. So which is our zero junction that we just talked about. And so basically series, you can say some in some sense. So series connection is you can say, you can call it as a zero junction. So
So series will be one. So
uh, yeah, sorry, yes, you're right. So it's sorry, I'm sorry. So basically the series connection will be a one junction, you're right. So because it's a common flow variable thing, whereas these two, if these two resistors like they are in parallel, so let us say we call them as R1 and R2. So how do we draw the bond graph for this? So like, let's say if we have a, let us say some voltage source over here, so then we show it as a source effort, and then basically this is being connected to a, so this is supplying some current, let us say I1, and this is being distributed into two branches across. So across R1, let us say it is I2, and for across R2 it is, let us say, I3, and here let us say it is across the inductor and capacitor, it is, let us say, I4. So I1 is being split up into these three parts, right? So the inductor and capacitor, they are connected together through a one junction. So how do we represent the like one junction? So let us say we write the number one, and let us say we draw these two bonds, let us say E2, E3. So as a matter of general convention, we usually write like the bond in this way, like, the effort on top and flow variable on bottom, or there may be other conventions also, but I generally am following this convention. So so what we will say is that in our one junction, it's basically the flow variable is common, so f1 is equal to f2 is equal to f3, so which is same as basically series connection, and the voltage E1 is basically sum of E2 plus E3. So like, since our flow variable is basically equal, f1 is equal to f2 is equal to f3, so we will be basically like, what is the equation like for this connection? So since this is a equal flow kind of connection, so we can say E1 F1. So in terms of power, we could write it as basically E1 F1 is E2 F2 plus E3 F3, right? And so basically our for this junction, so as a general rule, so we have this as that, uh, so it has only one effort equation, which is E1 is equal to E2 plus E3, and the flow, since it is equal, so it has, like, let us say if there are n bonds over here across this junction, so then it should have like n minus 1 causality bars. uh, so that's why we put the causality bars on the left hand side over here, because the flow variable is, like, let us say, known, and it's our input, and the output is basically E1, which is the sum of E2 and E3. So it's like saying that our the flow variables given on this for this bond, it's our input. So that's how we assign the causality for a one junction. Now to draw a bond graph for a system like this, so we just started, like, we start with a source of effort, and then we see that this R1 and R2 are basically in parallel. So parallel is analogous to a zero. It's basically analogous to a zero junction. So then we show this R1 and R2 are basically connected to this zero junction. And this is also further connected to a one junction which has the inductor and capacitor in series basically. So we can show basically that our bond graph would look something like this. So does that make sense?
Yes, sir. Okay.
Okay. So now we come back to our original problem that we were discussing, that for assigning causality. So here we are, so is everyone able to, is everyone able to see my screen now?
No, sir, we cannot see.
Okay. So I think now you will be able to see, right?
Yes, sir.
Yeah. So let us come back to our original problem. So now we have a certain bond graph given here, and now how do we assign the causality here? So based on this, whatever we discussed, so can we draw some causality bars?
Yes, sir. Yes.
So how do we start with now?
Start from there, that point, sir. Yes, because the source of effort is giving their input on there.
Yes, yes. So the source effort, the other end of the source effort would be basically the where we put the causality bar. For an inductor, we put the, so for, like, let me draw just here again. So for an inductor, the general causality bar would be something like this, whereas for a capacitor it would be something like this.
Yes, sir.
So based on this, we could assign the causality like this. For every inductor and capacitor. Okay, so now we have this one junction and zero junction. So now then in this case we have the like we, based on basically our the things that we discussed about inductor, capacitor and source, so based on that we are done with assigning the causality. Now we have some flexible elements like the resistor and transformer. So TF is transformer. So for the transformer element, our causality bar is again, there is some flexibility in assigning that. So it could either be, like, so like it's a two-port element. So therefore either we could assign the causality in this way, or we can assign it this way. Now this we have to select based on the type of junctions that we have, like in the adjacent, the junctions which are adjacent to this transformer. So since this zero junction already has a causality bar over here, we should not put any more causality bars across here on this part. So for this bond, the causality, so if we work backwards, so then this means that this causality bar should be here, and correspondingly the other causality bar should be here, right? So that also satisfies the rule for the one junction. So now we are left with one more element, which is resistor. So since the inductor bond is like that's a strong bond, so it would supply the flow to this junction. So then the there will be one more causality bar which we need to assign over here at this resistor on this side. So this would complete the requirement of having n minus 1 causality bars across the one junction. So this would be our somewhat a sequence of assigning the causality bars. So is that clear?
Yes, sir. Yes.
Okay. So now, based on this discussion that we had, so about how to draw the bond graph. So the question that we have next is basically we have a electrical circuit, and then uh, we have to draw its bond graph. So let us try drawing this bond graph together. So I'll give you about, you know 5 minutes or so to think, and we'll discuss in, like, let us say 5 minutes or so, or maybe I'll just give you 2 to 3 minutes to say to think about this, and then we'll just come back and discuss. Okay. So we'll discuss after 2 minutes. So till then we can think about how to solve this. So I'll leave this slide open till then. So any idea on how do we start solving this?
So we can start from the source of effort first,
Okay,
and then we can say zero junction.
okay. Then
Zero,
okay,
zero, zero junction for R1.
okay,
Then again we can put one junction for L and R2.
okay.
Again zero junction for C2.
So R2 and C2 are actually in series, right?
Yes,
So
sir. Yeah.
so
So
then which type of junction would they be connected by?
then we can say zero C2 and R3, sir. C2 and R2.
C2 and R C1 do you mean C1 and R3?
C1 and R3 actually they are parallel, so I think it should be zero. 1, it should be 1. Yes.
Any more thoughts on how we can proceed?
So from starting, sir, again, yeah, source of input to 0 junction for R1.
Okay.
Then again, 1 junction for L1 and R2.
Okay. Just hold on for a moment. So I'm just putting up my Jamboard for.
Okay.
So this is our circuit. So yeah. So as Vishal, so you were mentioning, so we start with, let us say, this source.
Yes, sir. From source of input to 0 junction.
Okay.
Then in 0 junction, R1.
Zero junction for R1.
Yeah.
And
And we move to 1 junction from there.
okay. So see, so there will be like, so this current, let us say there will be current I1 flowing across, let us say, this loop inside. So and let us say if I2 is the current flowing across this loop, so the it's like basically being distributed. So let us say the current through the inductor branch is, let us say, I3, and the uh, current flowing through R2 and C2 together is, let us say, I2. So that means that R2 and C2 are like the same current is flowing through R2 and C2. So what junction do we represent them by?
0.
No, it's zero junction is for equal effort, or basically, so equal effort or equal force variable. So it's basically for a series, for a, sorry, for a parallel connection. Just a moment, there is some problem with my screen sharing. So if the same current is flowing through R2 and C2, then we have to represent it as a one junction. So, right?
Yes, sir.
Yes, sir. Yes, sir.
Right. Now, the combination of R2 and C2 and this inductor L are now in parallel. So now the junction, so this point which across which the current is being split, so that is basically a zero junction. So then so we can represent now this as a, or we can just simply write it as L. So this is our zero junction now. Now, so the whole this thing R1 and this combination of R3 and C1, they all three are in series, right? So then how do we write that now?
Using a one junction.
Yes, so we will use a one junction. So first of all, the R1 is just simply just connected to the one junction directly, and in addition to that, this current I1 is flowing through this combination of C1 and R3, which is in actually parallel. So now since it is parallel, it is now we can use a zero junction, right? Since it's a parallel connection, so for series we will use one junction, and for parallel, since the voltage across C1 and R3 is the same, then we represent it as a zero junction. So then we can draw bonds like this. Let us say R3 and C1. So across the one junction, what all is connected? So basically R1 and then the combination of R3 and C1 in parallel, and this thing, the big thing, like basically the inductor and R2 C2 together. So that is also connected. So then we can draw a bond simply like this. So that will complete our basic bond graph, right? Makes sense?
Yes, sir.
Okay. Now how do we assign our causality bars now?
First, we assign for the source of effort.
Yeah. So which side should I draw the
On
causality
the
bar?
arrowhead side. Arrowhead side.
This side, right?
Yes, sir.
So let me just take a different color. So the causality bar will be somewhere here. Now next we know for inductor the causality bar, how it looks. So for inductor it's on the right hand side, whereas for the capacitor it's on the left hand side, right? So based on this rule, so let's put the causality bars here, and for the capacitors C2 and C1, so let's put it here and here. Now here, now how do we proceed further now in assigning the causality? since we have resistors R2 and R3, for them the causality rule would be flexible. So then we will be assigning the causality to them at the last. So but before that, what else do we need to consider now?
So we have to write like SF also, no sir? SF.
Sorry,
Source of flow we are not writing, sir, here, right?
source of flow.
Yeah.
We have a source of voltage. Since we have a voltage source, so that's why we are writing voltage source here, right? So like effort, source of effort. Now since we have let me give you a hint. So we have zero junction over here and some one junctions over here. So since in the zero junction, since we already have assigned causality to the the capacitor element here, so there will be no more causality bars on this other ends of the causality, like the bonds. So then, so for this bond which is joining the junction 1 and 0 junction over here, between the basically the which is connecting the SE and R1. So for that the causality bar would be here, because it cannot be on the lower side. So we can assign the causality bar to this R1 over here. Then how do we proceed further now? So for this resistor, since we have already assigned the causality for this zero junction here already for this, so the causality for R3 should be of this type. Now how do we proceed further? So we can basically either put our bar either here or here or here or here for the or here and here for the remaining elements. So we have to, so let me change the color. So we can either select the green set of bars or blue ones, right? So is it visible like whatever color that I have drawn? Is it clearly visible?
Yes, sir.
Okay. So which set of bars we can select? Any idea? Okay, so I think maybe you can think about it, and in the meanwhile, in the interest of time, let us. So I think I would suggest that you make you can make a note of this thing, and we can discuss it in the next session or at the end of the session if we have time left. So let us move on to another problem for the time being. So now let us take up the next example where we have a mechanical system where we have like two masses M1 and M2, and they are connected together by the spring K1 and the damper R3, and so the force is applied to the mass M2, and it is also given that there is viscous damping between the mass M1 and the surface, which is given by R1, and the viscous damping factor between M2 and the surface is given by R2. So now again we have to make a bond graph for this system now. So again I'll give you like 3 minutes, let us say 3 minutes to think about this problem, and we'll come back after, like we'll discuss again after 3 minutes. So we'll discuss at 8:30 now. So it's 8:27 now. So let us now continue our discussion on this problem. Now, since we have a mechanical system, uh, we can look at the analogy of electrical analogy of the components, and based on that, like the analogy is in terms of series, parallel, etc. And so let us start constructing uh, the bond graph model for this particular system. So how should we proceed with this? Any idea? How should we start drawing this bond graph diagram now? So any idea how do we start solving this problem?
We'll start with source of effort, that is force.
Okay.
Uh, Connected to a zero junction, we'll consider M1 as inductance inertia and M2 and R2 to be in like parallel circuit, and
Okay.
then connect that to a one junction with K1 and R3, that connected to an again zero junction with M1 and R1.
Okay. So have you tried to draw the uh, the kind of the bond graph diagram yourself?
Ah, yes, sir.
Is it possible for you to share your diagram somehow, like maybe in the chat, or suppose, like, I don't know, I mean, whether you can share images in the chat or
Even I'm not sure, sir. I drew it in the book, so.
yeah, yeah, exactly. Okay, fine. So yeah, so let's start. Let's proceed as per what you said. So we'll go step by step. So we look for let us not jump to which junction. So let us first identify what are the let us now first let us say this is the variable, let us say x1 x2, that describes the position of this two masses m1 and m2. So those are the two degrees of freedom, so to speak, for this system, right? So it's 2 degree of freedom, so the masses can move independently with respect to each other. So now, so there is a velocity of this portion, let us say this is x1 dot and this is like x2 dot. So the velocity of this mass m1 with respect to this surface is x1 dot. So there will be a viscous drag force on this mass m1. So let us say if the velocity of x1 dot is like this way, then the drag force will be acting somewhat this way, and the for the mass m2, let us say if the velocity x2 dot is this way, then the drag force would again act this way. So which is let us say r1 x1 dot, and this is r2 x2 dot, right? And in addition to that, there will be the spring force. So let us say that is like we call it as Fs. So this will act on both the masses m1 and m2, and similarly this force by the damper. So the same force will be acting on both the two masses. So therefore K1 and this R3 are in parallel, and the velocity at the two ends of this K1 and R3 are basically constant. So the spring force will be proportional to like basically x1 minus x2, and for the damper force it will be basically R3 into x1 minus x2 dot, x1 dot minus x2 dot, basically the difference between them. Now we can take the help of these equations to get some idea of how to now visualize this or represent this thing in terms of a bond graph thing. So uh, like physically these ends of the masses m1 and m2 are the physically the junctions which at which the spring and damper are joined, and like this r1, this damper r1, we can also like represent it in a way where we can say that the velocity of the um, basically the mass and the damper share a common velocity. So I mean it's like basically the mass m1, so we can write it as a inertia element or some which is analogous to an inductor. So the bond for m1 we will draw it like so it's basically inductor which has a mass inertia value of m1, and similarly for m2 we will draw it like this. So so the uh, what I mean to say is that the velocity shared by this damper m1, this the damper r1 and this mass m1 will be the same. So we can represent it as a one junction because they have the same velocity or same flow variable, or in some sense they are they are in series in some sense. uh, so we start with this source of effort which is force, and now the mass m2. So let's draw a one junction, right? And we'll draw two bonds. So one which represents this mass m2 or inertia element, basically inertia or inductor kind of element, which is basically mass m2, and the damper element. So we can write it as a similar to a resistor. So Lakshmi, is that what you have got also?
No, sir, I had interchanged the junctions. I had got confused with the junctions.
Okay.
I understood this.
Is this correct whatever I'm drawing, because I am also just drawing along with you only. So is
Yes,
this
I understood.
yeah. Then now we have this combination of K1 and R3. They are connected in parallel. So we need to have a zero junction now to basically since the ends of the two the masses m1 and m2, they have a common velocity, and at the same time they are these two on both ends, like these masses are subjected to the same spring force. So we need to also have a common effort junction, and on top of that we also have this combination of K1 and R3 which is actually in parallel. So the uh, K1 and R3, if we just look at K1 and R3 separately, which are in parallel, so K1 and R3, and Now, how do we represent them, their bond graph? Now they are in parallel, right? So, what type of junction do we use now?
Zero junction.
Okay. So we'll put a zero junction here. And similarly, there will be another one junction to which we will have this similar inductor element and the damper R1. And to this branch, we will have actually a one junction, right? To represent K1 and R3. So let me just draw it again because it's too much of clutter. So we should have a zero junction to represent K1 and R3 because they are in parallel, right? And this combination of the M1 and M1 and R1 and M2 and R2, they are also in parallel with the combination of K1 and R3, right? So I think this should be the final bond graph for this. So is this correct?
So can we reduce the two zero junctions into one only by adding it adding R3 and K1 directly to the first zero junction?
Um, See, basically uh, the this the element K1 and this R3, they are subjected, like the velocity at their ends is common for them, both of them. So common velocity or common flow junction uh, is is actually one junction, right? So it should actually be one junction here. I'm sorry. Uh, so yeah, so they are not actually two zero junctions. They are actually, there is a zero junction because this mass plus damper R1 and then mass plus damper R2 and this combination of R3 and K1, they are together in series, right?
Yes, sir.
Right. So that's what I think the how the bond graph should look like. So anyone have got any other answer? If not, so I think this was the this was about this problem. So then we have some couple of more problems also left to discuss, which I think you can uh, you know take up them as you can try them on your own. I will just maybe go over it once briefly. So in the interest of time, so since we already discussed an example of how to draw the bond graph for mechanical and electrical systems, so we have kind of discussed both the the examples for both the domains. So hopefully that helps you understand how to go about the general process of drawing the bond graphs. So we have another example where we have an electrical circuit, so it's slightly more complicated electrical circuit. So you can try out drawing the bond graphs for this example. So here we have basically a voltage source E of t, E, and so then we have further multiple components like inductors and capacitors in parallel. So we can just go about the similar approach of like identifying the different loops inside the circuit and which particular combinations of components are appear to be in series or parallel, and then accordingly assigning junctions for uh, this thing. So based on that we can draw the bond graphs for this. and we also have so this example, and I can also share a couple of more examples for you if you want. We can try to solve them uh, later in the next class also. So based on whatever content that has been covered till now, anyone has any questions or comments?
No, sir.
Okay. So, Vishal, I think since you had asked some questions earlier, so did this session, whatever content that we have covered so far, has it helped you in understand the things better? Like, so do you want me to go over this example also, like the one that I showed? So shall we go over this example also?
So we'll try to do it.
Okay, fine. So then I think you can try to do it, and then we can also we can discuss it in the next class and in the next session. So I'll also share the recordings and the slides, and I'll also try to share some more examples that you can try on your own. So hopefully that should help you. Anything else? So I also had one more example where we have like a current source instead of a voltage source. So we usually, we have so far we have discussed only the examples with uh, only with a voltage source, but we can also have an example with a current source kind of thing for an electrical system. So maybe like if you like, let me just draw an example for you. So like this, like let us say this is a current source, and let's say you have this thing a resistor R1, and you let us say also have a voltage source in the same circuit, and let us say some capacitor, inductor. Let's call this as R2. So then now here we actually have now two sources. So how would the bond graph look like? So it would be like, so source flow, and then we'll be having a, let's say, a one junction, or it's actually not required. The one junction is also maybe not required. So since the combination of like this R1 and this voltage source plus capacitor, inductor, and R2 together, like all these things are in uh, series. Oh, okay. Sorry. I think I forgot to share my screen. Sorry. Uh, okay, let me share my screen once again. Just a moment. Yeah. So we have this basically voltage source as well as current source here, and now if we just want to quickly look at how to draw the bond graph for this. So so there will be some current I1 here which is supplied by the current source. So then there will be the current across resistor, let us say it's R I2, then across the voltage source, let's call it as I3, across the capacitor I4 and I5. So the inductor L and R2 are in series. So there for that we need to use a one junction. So basically, so so the inductor and L and R2 would be it's in series. So because the same current is flowing, and both the combination of L and R2 and the capacitor C, since they are in series, we can represent it as a zero junction. And we have a source of like voltage source. So let's call it as SE. So there will be some current that is supplied by the this voltage source. Let us say that is I3, and so because the current is being split, um, the current I1 is being split into like I2 plus I3. So we'll have a zero junction here. So the current that is flowing here will be I1, and current flowing over here will be I2, and the further current I3 so now the current I3 is uh, flowing across this voltage source, and at the zero junction over here, so let's call this as A, this is B, so this corresponds to A and this corresponds to B. So the current I3 is now splitting into I4 and I5 over here. So now the junction that we should use is a one junction here, because the same current is flowing from by the voltage source as well as from this bond. So this is how we can like draw the bond graph where we have two sources. So this was another kind of an example. So similarly, you can try out more examples. So I'll also try to share more examples in the slides that I'll upload. So I'll also be uploading the recording for today's session as well as the previous week's session. So please go through it and let me know if you have any questions in the content covered in this week as well as previous week. So that's all that I had from my side for today. So thank you all for joining. So was this session helpful?
Yes, sir. Thank you, sir.
Yeah, thanks. Thanks all for joining.
Thank you, sir.
Yeah, welcome. Yeah, welcome.